I'm going to share my screen. Okay, you can see my screen, right? Great, yeah, so I have Excalidraw open, which will help us work through things. But I think the first thing we could do, we have a little time. Hopefully, if we have time, we can touch on the depth first versus breadth first search. But that can take a little longer to implement. And also, I think one of the issues is that visualizing a tree can often be really difficult, like in code. So the first thing I want to do is let's really focus on the linked list thing. And I have some stuff here, but let's actually just create a new file. So I'm going to say new file. Suppose I could call it linklist2.py. Doesn't really matter. Just want to be able to run it. But look, it's right there. And one thing we could do while we do this is actually walk through like what. So if I go like linked list wiki. Okay, so we're looking at linked list on wiki. It tells us a little bit about how that looks. So we have like this, pair here with a value and then an arrow that points to the next thing. And that keeps happening until we point to nothing. So that's a standard singly linked list. There's also this example of like a doubly linked list. There's other variations, but the singly linked list is the classic example, and that's what we want to work with. And when we look here, we see that it says like there's a couple of common operations we might care about. So kind of with anything that's about like storing data, especially in comparison to an array, we care about something like peak index. So peak just meaning given an index, can we see what is at that element? And you see here it says, this is not actually O, this is something else, but essentially this is big O of N for peak, meaning we might have to look at every element. And then there's this idea of mutating. So for arrays, they're not really showing anything about mutating because an array is really fixed size, whereas a linked list, we can always add to it because as long as there's memory somewhere on the computer enough to fit a single additional node, we can add to, delete, whatever we want. And there's different guarantees whether you're adding to the beginning, the end, or the middle. So I think what I want to do is focus on getting some of these operations. So creating the linked list, figuring out peak, figuring out adding to the beginning, figure out adding to the end, and then figure out things like inserting somewhere in the middle and or deleting somewhere in the middle. And we'll use some like stuff we draw to see that as we go. So first things first, I can't make a linked list without making like a node class. So I'm just going to call this node. And we're going to do a def init. And what should this node take? So ultimately, a node is just this. We want it to take something like value. And we also want it to take something like next. And value is going to be something like a number, and next is going to be an arrow that might point to another one of these nodes, but could just point to none. So what do we want to pass into this node we're creating in order to, create this basic little structure here?
We could pass val and next.
Yeah, exactly. So I'll just go with what you said. We're going to call it val. That seems to be common, and next. And then we actually want this to live in the, in the instance of this node itself. So we're going to say self.val equals val, and self.next equals next. And this is a way to do it. Let's say we wanted to actually print this. I could say something like, okay, well, what if I wanted to just see that I could create one? I'll say, lowercase node equals big node, and I'll say 1. Okay. And I'm already noticing, well, I passed it the 1. I would have to say something like none here to define what this is. And then I want to print it. And I'm going to print node. And if I run this now, I say like Python linked list 2. All right, that's what it prints. And I kind of don't love that it prints that. So maybe I'll do something like def underscore underscore string. And that's going to return a string. And what will it actually return? I'll say something like this, like, given that this is a node, I'm going to return one of these f strings. And inside, I'm going to put the self.val, but we need to put it in here so that it's actually represented as a string. So self.val. Any questions on this part, the repra? This is just going to take what is a number or something else and convert it to a string. Yeah, the chat real quick. Yeah, and Eric has mentioned that we can give this next a default parameter of none, because what I want to do here is say, okay, well, when I print one of these, I want it to point to, well, it's ultimately going to point to the next one. I want to do that outside. But what is that next one? Well, if the next one, so in this case, it's just going to look like this maybe. And so if I were to run this again, that's what it looks like. But maybe I have something like I want to print node 1, which points to node 2, which itself points to none. And at this point, I'm basically creating a little linked list here. I could call it linked list. So before we even make a linked list class, this is enough. This is a linked list. We just have a single node, and it has a 1, and then its next is a single node, and that's next is none, and then we're done. So if I have this, though, I'm still just, it looks like 1 dash. And I can see how eventually I'm going to want to like print each node. But maybe I'm going to want to do something where when I print, node 1 and that has something else in it, I just want to print that. But if I print node 2 and its next is none, I actually want to print that as well. So I might have something like this where I say, I wonder, can I write this right in here where I say something like, maybe I'll say like end. How do I, it doesn't seem to.
We could just do self.next.
Well, exactly, as in, well, I mean, I normally would make this within the, I normally, what, ultimately, I'm not going to put this in the node class. Why make a node into a string? I'm really not going to work with nodes. Let me take this out for now, and really, I'm just going to work with linked lists. So for right now, we can't really see our linked list when we print it because I don't have any kind of toString. But I could say something like, okay, let's say I have a linked list. This is what it looks like. There's 3 elements in there. If I wanted to print it, I could do something like, I could say, this is sort of the standard thing. I would say current equals, linked list, which refers to the head. And then I'll say while current. So while current is not none, I could be explicit about it and say while it doesn't equal to none, I'm gonna print that. So I'll say print, and here maybe I want that f string where I say print current dot val, and I wrap that in the repra. Is that right? Yeah. And then I have an arrow there. So I'm gonna actually, maybe I don't even want to print it. I'm gonna do something like, I'm gonna build this up over time just to show you what that looks like. So I'll say linked list as string equals an empty string. And then I'll say while current does not equal none, oops, linked list as string plus equals this f string, and this f string is going to look like that. So it's going to print 1 arrow, and then I'm going to update current. So I'll say current equals current dot next, and as long as that current, the new current, is not none, it should print the value and keep doing that. So if I have something like this, what I have right now, let me just copy that, I guess. That's what the basic thing looks like. Make this a little bit smaller maybe and take these out. So it's sort of like I have LL and it points to this first one. And in that first one is a 1. Let me get that right. In the first one, we have a 1. Let's make that larger. And we're just going to have multiple of these. So like that. And honestly, I can make this a little smaller so that it all fits. Downsides of doing this in real time with Excalidraw. Ugh. So over here, I have my 2. And then finally over here, I have my 3. And that last one just points to none, which, you know, if we want it to be explicit, we could actually write out something like none. Okay, so this is what I have. I have linked list points to that node, and its next points here, and its next points here. And while current does not equal none, I'm going to print out essentially the number and an arrow. And I keep doing that, the number and an arrow, the number and an arrow. And then when it's all done, I should have a 3 arrow. And so what I want to say is when this while loop is done, while loops can have else statements as well, I believe. At that point, I'm going to say link list as string plus equals just the word none. And then I am done. So at that point, I will print linked list as string. And let's see if that works. Yeah, so that represents our linked list. And this works, but at a certain point, we kind of like, if we want to work with a linked list, we don't just want to work with nodes. We want to work with something that understands we have nodes pointing to nodes pointing to nodes. And so it kind of makes sense to actually create a linked list class and then to take some of this logic and move it in there. So I think what I'm going to do first, right under here, I'll say something like class linked list. Make that a capital L. And just open it up. And I'll do a def __ init. Take that out. And then the question is, what should it actually take? It could take something like it could take the first node, but I think what I want to do is I want to make some kind of like append function. And so initially I'm going to say it takes nothing. But then inside I'll have a self.head. And that will initially just point to none. So now we're going to replace this out here. And we're going to get this back pretty soon. But I'm just going to replace this with linked list itself. And that's all there is to it. So none of this actually exists right now. I just have a linked list. And of course, if I were to print that linked list, that wouldn't be very useful for us right now. It's just going to show that. And I want to add back in this feature where we're actually able to like look at stuff. But before I do that, I want to add an ability to add things, right? So I think the first thing I'm going to do is do something like append. So we're going to have an append function here. And append is always going to add something to the end. So we can sort of imagine this LL now doesn't point to anything like this. LL, like this doesn't exist yet. Let's just put it up here for now. LL points to, you know, this object, and that object might hold on to multiple things. But the only thing it holds on to right now is something called self.head. So I'll just write head in here. And that points to none. That points to nothing right now. And then maybe we'll add stuff to the linked list. But for now, this is all we have. So I have self.append. Well, if we want to append something, if we want to like create a new thing like this one, we're going to need a val. And that's all we actually need. Okay, so now we're at this point. We're trying to add our first element to the linked list. I'm trying to run append. So when this is ready, I'll say ll.append 1. And at the end of it, I would expect it to have a 1 there. And maybe I'll make a couple things here. So I'll say 2 and 3. And then ultimately, I'm going to want to print that LL. So if I can get all this functionality, that sounds pretty good. So for append, this is exactly what it is right now. That's all our LL looks like. It's a linked list, which has a head, which points to none, and it's blank. So if I wanted to append one, what should I do? What's the first thing I should do here? We might track the tail eventually, Eric, but first things first, I have a val. What do I want to do with that val to make it useful in terms of a linked list? So I have this right here. Let me disconnect these. I want to create something that looks like this, right? As in before it's even connected to the linked list, I want to create some kind of node for that thing I just passed in. So I
we
guess
need to make a node.
say that again.
So we need to make a node. We need to create like a variable and then assign it node val.
Exactly, yeah. So the first thing I'm going to do is I'm going to say new node equals node, and I pass in that val. So now I actually have something just like, linked list point somewhere. Okay, I got a variable, and that variable looks like this, but it doesn't say linked list. It says new node. But notably, new node is not connected to my list, right? So how do I want to connect it to my list? I currently have head, it points to none.
Be like self.head.next equals new node.
Yeah, sort of. I mean, that is one approach, but notice that head is not even a node yet. So I think we might end up needing a special situation, but for now, we just want to say something like self.head is equal to new node. And now head points to new node. By the time this is done running, we don't see new node anymore. And now we technically have a linked list. But you could probably see there's going to be a problem here because what happens when we try and add two? We try and run the same code. Okay, well, I create this thing called two. I don't know why they're up there. I create this thing called two, and I point new node to it. But I don't actually want to point head to new node because that would mean this, right? So there's a couple ways we can solve it. How do you think we should be adding something to the end there? Might not be giving you guys enough, which is why I think the first thing I'll do is I'll say, okay, if we want a special case for this thing where we're adding the first one. And we're going to have to keep track of that when we remove things too, because if self.head is none, it means there's nothing in the list. But that's a pretty unique case. So I'll say if this is the first thing we're adding, i.e. if self.head is identical to none, then we want to do something like this. We actually want to set self.head to point to that node. But what if that's not the case? So right now we're in the case where, we created this new node either way. Self.head does not point to none. So how do we connect this last node, or this only node that exists, to the new node?
Would it be self.next?
We could do that. Yeah, we could say something like, okay, well, in that case, we actually want to take self.head because it exists, and then say .next equals to new node. So let's go with that for now. We say self.head. So self.head points here. Its .next points here. So we set up its .next to point to 2. And so right now, this kind of looks like this. I really got to group these things. Okay, and we'll move all these. And now new node's not here, but now we get to the point of saying ll.append 3. Okay, once again, we create this this new node called 3, and we want to hook it up. So what do we do in this case? how do we append to the end of the list? We have the head. We say, okay, head points to 1. We could say something like, we could actually, iterate through it until we get to the last. But at this point, it kind of seems like we should keep track of one more thing, not just the head, but actually whatever the last element is. That's a good thing to keep track of. So I'm going to add that up here. I'm going to say, okay, initially, not just is self.head equal to none, but I'll make something called self.last, and that's equal to none. And that's another thing that when we start removing things, we're going to have to care about this situation too. But I'll say like, okay, if we're in this special case where self.head is none, then I set self.head to new node. And otherwise, so I set self.head to new node. And at the same time, I'm going to want to say self.last is equal to that new node. And then in this case, so now let's say we didn't add the 2 yet, we're just adding the 1. So we see, initially there is no 1. And then we say self.head is none. Okay, then point head to that new node, but also point something called last to the new node. So I'm going to put something called last here, and we have another arrow. And last points to the exact same node. But now let's say we're running it a second time. We're trying to append 2. Okay, we created this thing called 2 here. Now, how do we hook it up? Well, now we can just say self.last. So that's going to point to the last thing that exists, which is this 1. Its dot next should equal the new node. Okay, I'm starting to like this. And that will work. But again, we want to update last. So we got a point last there. So, we have this as well here where we say self.last is equal to that same new node. And then when we append 3, we see the same thing. So let's see if this works. We create the new node. We see that head is not none. So what we do is we say, okay, well, go to self.last, which is this 2, go to its next, point that to the new node. And then last will also be reset to the new node. And what we can start to see is, okay, because we're doing this in both cases, really don't need it in both places. I'll just take it out of there and then have something like this. So I'm making this new node. Maybe I even do that first, where I say something like, I have this new node. Self.last always is going to point to that new node. And then in the case where head is none, self.head should point to the new node. Otherwise, I see, I actually don't want to do that. I want to take, okay. So I do want to put that at the end, I'm realizing, because in the case where head is none, I do want to set self.head to new node. And otherwise, I want to set, whatever the current last is, it's next to new node. And then this line, I want it to come after because it actually resets what last points to. So any questions on that so far? Like where we added 2, we made a new thing, or sorry, we were up to here, we added 3, we made it a new thing, and then we went to self.last, we followed its next, and that now points to the new node. And then we take self.last, which currently points here, and now we point it here. So in this way, we're always adding something to the end, and it's like a simple one operation. Okay, any questions on this so far? If not, the next thing I'm going to do is actually write that print statement, because I want to be able to see my lists as I print them to make sure they make sense. So we call it string. It takes self, and in this case, nothing else. And we're going to follow pretty similar logic to what we had down here. So just copy paste this and put it in here. So yeah, first we have, current, which is going to keep track of what we're looking at. But I don't want current to point to the linked list. That's not a thing. So I point it to self.head because that's the beginning of the list. And similarly, I'm going to keep track of this string that I build up. So I'll call it linked list as string. And then I'll say while current does not equal none, because if current equals self.head, initially, it would just equal none. But I'll say while it doesn't equal none, what I want to do is I'm going to update that linked list as string variable to include currents.val and a forward pointer, or forward arrow. And then I have the same thing here. I say this is, I'm going to update current to current.next, which is going to keep this loop going. And that loop is going to keep going until current itself is none, which will happen when we go from 3 to nothing. But it would also happen if head itself just equaled none already. We would just skip this while loop entirely, and we'd come down here. And here I just add, none, which will come at the end here, but it would also be by itself if there was nothing in there. And then finally, instead of printing it, I'm going to return it. Okay, so I like that. And what I'm going to do now is I have linked list here, and I'm just going to want to print it at each stage. So I'll have something like this. And now let's run it to see if it makes sense. Oh, we did something wrong, so that's good to know. Nodes init is missing one required positional argument. Next. So that's something I actually didn't ever take care of, which is this node here expects that I give it a next. And when I'm creating these, when I'm saying ll.append1, if I look here, when I create a node, I'm not doing that. So I could do this, and now everything will work, I believe, and that looks good. The list starts out as none. I added 1 to it. Then I added 2 to it to the end. Then I added 3 to it to the end. But as someone mentioned in the chat, that's kind of overkill. If this is going to be a common case, let's just make the default none. Okay, so now we basically have a working linked list in that it's a linked list. I'm able to append to it, and that append is constant time because we're keeping track of the last node. So it's always a single operation to just, attach from the last node next to the new node, and then reset the last node to that new node. So we're always keeping track of that last node. And then when I want to print it, that's ON because I have to walk through the whole list, but that's kind of expected. Even if you were printing an array, if you have to touch everything, that's going to be ON. So this works right now. And so any questions where we currently are? In terms of our linked list, we're able to append to it, and we're able to print it. Okay, we seem to be on board with this. So if I were to look at that wiki article, one of the things it mentioned was peak, which is like index. So we already did this adding to the end. But the next thing I might want to do is I want to create this peak thing, which that's just going to let us see the value at a specific index. So I'll say self and I'll say index. And we'll test it out like this, where I'll print something and I'll print the result of ll.peak. And I want not the 0th element, not the first element, but the second element. So I would expect this to be 3. And that's not going to work until we actually fill it in. So the way we're going to do this is, we don't actually know. We can't just jump to that second element. So what we have to do is actually walk to it. And we'll do something pretty similar to this. We'll say current equals self.head. So we're always going to start at the head if we want to walk through the whole list. And then I'll say while current does not equal none, which I could just say while current, but this is more explicit. So while current does not equal none, well, first I want to check if I'm where I am. Well, how do I know where I am? I probably want to keep track of some kind of like count. So I'll say count is equal to 0 initially. And I'll say something like, I'm looking for a certain index. So I'll say, if count is identical to the index, so let's say I was looking for index 0, then at that point I would return current.val. And that is enough for us to see the functionality of something like, let's say I wanted to just peek at that first one, this should work. I see 1. But if I wanted to do something like this, like peek at the 1th element, well, currently I say I'm looking at that first one is 0 equal to 1. No, it's not. So this is going to end and the while loop is going to continue, but I haven't like reset anything or updated anything. So the first thing I'm going to want to do is add 1 to count. So after we look at that first one, we want to move on to the second one. So we add 1 to count. And then we also update what current points do. So current is now going to equal whatever current.next is. And if that's none, this is going to end. But if not, we will continue. And so this should work now if I try and print, 0, 1, or 2, should manage all of these. Okay, and it is able to peek at all of them. But as you could probably imagine, I could give it some bad data. Maybe we want to handle that. So for instance, if I give it peak of -1, what's going to happen? Looks like we got none, which kind of makes sense. I wonder why. I peaked at -1. Count was not equal to -1. It never will be. And then it was when this whole thing was done, I guess it returned none. And the same thing would be true then, I guess, if I tried to print the 3rd element, of which there isn't any. Yeah. But at that point, maybe I want to actually put stuff in there. So just like you can't index into an array somewhere, that doesn't work. Maybe I'll have some guards here where I say like, first things first, before we even walk into this function, look at index and say assert, which will essentially break the program if it's not true. And I'll say assert that index is, greater than or equal to 0. And if not, I will print can't index with negative number. So let's see that working now. Okay, what actually happened there? Yep, so basically we tried to run ll.peak -1 and it didn't like that. It said assert index greater than or equal to 0, can't index with negative number. So that's the functionality of assert. I guess because it must be a tuple because you don't actually wrap this in parentheses, you just put a comma there. And so we're going to take that -1 out right now. But still, let's say I try to look at that last one, we see none. So in the same way, I could say something like, okay, walk through it, and if count equals index, then we're good. But if we get to the point where count was not equal to index and current is now equal to none, we're now at this point, and we could say something similar where we say like, do we say assert? I don't even think I say assert. I basically just want to break the program. I want to throw something. And it's not so important we do this. So you know what? Maybe we'll just return a string in that case. In reality, we would maybe this is a good time for me to remember how try catch blocks work in Python. Does anyone remember if I look at try catch Python, this is an example of exceptions. And like if you index in Python into a negative try except, okay. If in Python I say something like array equals empty, and then I say array 1, I actually get an index error. So I get a specific type of error. And so the way we would do that in Python, we would have this try block. And the way it would work, it would try and run this whole program here. And then it might have an except at the end. So I'm going to have this try block. And let me see, how do I throw something? Raise an exception. Oh, raise. Okay, so I'm going to have this try block. And within the try block, maybe the first thing I would do is say, if index is actively less than 0, then we would raise something we're going to call index error. Can't use negative index. But otherwise, we would keep going. Current equals self.head. We run everything else. And then here I would do the same thing where I would say, if we got this far, maybe I want to do the same thing where I say, raise index error out of bounds. So, and then what do we do in that case? Can I just say raise? Yeah, I don't actually want to catch it. Okay, I think that actually works. So now let's try this, as in I'm not going to catch it, it's going to break the program. But if I run this again, the first thing that happens is when I do print ll.peak -1, we get this index error, can't use negative index. And so I will comment that out, and then I'll run this. And same thing, we get an out of bounds error here. But notice that if I actually, let's say I did this again where I, appended 4 onto there and I printed it. Okay, now when we run this, we added, we start with none, and then we have 1, and then we have 2, and then we have 3, and then we have 4. And now I was able to peek at all of them because now it's not out of bounds. Okay, that was a little bit of a digression maybe, but it's nice to see the try except raise stuff. So I'll take that out for now. Okay, so we have peek working, and we have append working, and peek just walks through each thing. So if we saw it on Excalidraw, the way that peek works is that we just go to the head and we keep track of accounts. So we can actually see that explicitly. If I look at my linked list like this, let's just say, we're working with the head there. So I'm working with the head here. Let's say this is my whole list. I'm just essentially keeping track of something called count. And I have something called current, which initially, so count will initially point, oops, get that out of there. Count will initially equal 0, and current will initially point to self.head, which could be none. But in this case, we have, current, and it points here. And then what happens is we say, is current none? No, it's not. So is count equal to the index? Let's say we're looking for 2. No, it's not. So now count plus 1. Okay, count is now going to be equal to 1. And current points 1 thing forward. And now count being, now we're going to do it again. Current is not none. The index of 2 we're looking for is not equal to count. So we do it again. Now we say count equals 2, and we move current forward. And now current is still not none. Count and index are the same, so we return current dot value. Okay, any questions about peek? Any desire to discuss why this is O of n? Or it's obvious? If not, I'm going to move on to something like prepend, as in put something in the front.
So I'm kind of confused on what's going on with that. It almost looks like it's a while else statement on lines 19 and 24.
Yeah, it is.
Oh, okay.
Yeah.
How does that work exactly? From what I understand, while just keeps going while it's true.
Exactly. So in Python, with both for loops and while loops, you can add an else statement. And the way that works is it says, while this is true, run this. But the first time this is not true, run this. And so the reason we're like, we could actually just take it out and do it like that. It's the same difference. But this is saying, well, it's actually relevant to the while loop. And if the while loop found it in there, it would have returned by now. So if the while loop actually finishes and we get to this point, it means we're out of bounds.
Okay, cool. I wasn't aware you could do that. So it's good to know.
Yeah, that's a cool thing. Most languages don't have that else at the end of for or while loops, but Python does, and I kind of like it. Because otherwise you do something like this, but the downside to this is one, it's not obvious that it's connected to the while loop in any way, and two, let's say the while loop like defines some value in it. In this case, I don't, but let's say I just find like x equals 1 or something. Well, I can actually access x equals 1. I cannot access it here. But if I were to have the else, anything I defined within the while loop still exists for the else. So it's a nice little convenience thing.
Okay, cool.
Yeah. So something else we might want to do, we have append, and that's O1. So we can add pretty easily to it, but maybe we also want prepend. So I'm just collapsing these in VS Code because it makes it easier to read. So we have append, which adds to the end, but maybe we also want prepend, and it's going to be pretty similar. And the question is, given append, can we write prepend? So right now I'm adding 1, 2, 3, and 4 in this order, but what if we wanted to add, like, I guess we'll leave those. No, we'll take the peaks out for now. We saw they work. So what if I actually want to do ll.prepend 0? And as a result, 0 would be the first thing in this list. How might I do that? Prepend. Prepend.
Would you reset the new node to the head and then head dot next to the previous head?
Yeah, perhaps. I need to think about it. So the first thing is we have that new node business, right? So I'll copy paste that from here. So the first thing that happens, let's say this is the current state of our linked list. We have the head, and let's also say that, last points here. That's not going to be really relevant for this method. But the first thing we do, just like here, we're going to create that new node. So that new node exists, and we put the 3 in it, and it itself points to nothing. So now how do we hook this up to the existing list? So all we really, basically we have head here, we have last, and we also have new node, which itself has a next. So my sense is, if we have a 0 here and we're trying to add it to the front, how do we associate this new node to the existing list? I'm going to do a little variable juggling. So I'll start us out, I guess. We have the new node. If I were to say something like new node.next, it's currently none. What might it make sense to point this next to?
The head, right?
Exactly.
Head, yeah.
Whatever head's pointing to, that's where we want new node to point to. So self.head. And that totally works. And in fact, even if head was none, that would work. But in this case, we have our new node. We want to point it to the head, whether it's none or it exists. Okay, that's good, but we're not done, are we? Because next time we run this, head still points to this element.
We need to set self.head to the new node.
Exactly. So head is always going to keep track of that first element. And because we added a new first element, this is what we want head to point to. So I'll just say self.head is equal to new node. And you kind of see how the order you do things in often matters. Like, well, in this case, I guess exactly. Like we wanted to first set self new node.next to self.head, because self.head was pointing to the original head before we updated it, and then we updated it, because if we did it the other way around, we would no longer have access to that thing. So I believe this works now. So if we save this and we run it, oh, I didn't print it at the end, so let's print it. So it works. Maybe I want to test it a little more. So I'm going to say something like, well, in this case, we have a linked list that's empty. So, and then we printed it. Well, what if right there where it's empty, does it still work? So let's say I append a 0 to something that's empty, and then, or I'll just do it like that. But I'm just going to change all those to prepends. So I just want to test it works in all cases, and empty is, an important case, but it does work. And now that we're adding it this way, we're kind of adding them backwards. Okay, so that is that is append and prepend, which is, that's sort of the standard case. But then we might have an additional case where we have something like def, insert at. So sort of similar to peak, we actually want to take an index. And now the question is, given this peak thing, can I insert something into, in the same way? So basically, if I have, a list that currently, let's like readjust these a little. Let's just say I have a list that, currently looks like this. There's no new node, but there is a head and a last. This is what my list currently looks like. And I'm going to say insert at 2, which means the second index. So basically, I don't want to insert here. I don't want to insert here, but I want to put something here, which means, like, let's say I said not just insert at index, but I would need to add a val as well. It's like if I wanted to insert at index to val 5, what I want to do ultimately is end up with something like this. My arrows are getting a little funky. So I want to end up with something like this, where I'm able to add some new node with a 5 in it. And I'm able to add it such that it's now the new second and everything else is pushed forward. So let's try and write that together. As you could probably tell, compared to append or prepend, we have no way of jumping right to that index. So this is worst case ON. But let's see how we might do this. And I guess for now, let's like not worry about indexing too much. As in, if it's a negative index, that's not going to happen. If it's too big, it's not going to happen. It obviously could happen. You would want to write that in the real thing. But for now, we just want to come up with something like ll dot insert at, and at index 2, I'm going to add a 5, and then I'm going to print that. And given what this looks like, I expect that, okay, this is my 0th element, this is my 1st element, this is my 2nd element. So I actually want it to look like 4, 3, 5, 2, 1, none when I'm done. Okay, so we're going to write this together. First things first, I probably want to walk through the list, right? So how do I walk through the list? We've done this a couple of times now. I want to walk through the list from the beginning, and I guess I want to keep track of a count. So I'll say count equals 0. And how do I walk through the list? What's a nice variable name?
Current node.
Yeah, so I'll just call it current in this case. We've been calling it current node. I just like current, so we'll go with current, but current is going to initially equal what?
The head.
Exactly, self dot head. So the first thing we have here, I guess I'll go back to before I added it. The first thing we're going to add here is we're going to have something called current, and it's itself going to have an arrow pointing to the same thing as head. And maybe it's that, maybe I want to actually insert at this first spot 0. But maybe not. I guess and that could get confusing with the whole head thing, but let's just say we don't, we're trying to insert at this second position. So we want to get there first, right? So how do we get there?
You do a for loop.
For loop or a while loop in this case?
I think it could be either.
Yeah, you're probably right. It probably could be either in some sense, but because of the whole current.next thing, I kind of like the while, where I'm going to say while current does not equal none. Because if it equals none, we're in a bad situation. We can't do anything else at that point. But while current does not equal none, I'm going to say current is equal to current.next. So that's how we move it forward. But we're also going to want to add 1 to the count. So it's like I'm here, my count is 0. Now, because this is not none, I'm going to add 1 to the count and walk to current.next. And then I'm going to add 1 to that count and add current.next. But this is actually going to continue seemingly until I'm at the end. So when do we want to stop looking at this? Like which node?
Count equals index.
Yeah, so something we could.
One
what?
before the index, right? Because you're gonna have to assign that one to. You're gonna have to rearrange them there.
Exactly. Yeah. So we were going to get to that, but that is true. That if let's say we update it until we find the index we want to replace, well, that's actually too late, because ultimately we're going to want to create some new thing that looks like 5. And 5 itself points nowhere currently, and the only thing that points to 5 is going to be a little variable like new node. But this 5 we have here, if we want to hook it into the list at that place, we actually don't want to stop here. We want to stop 1 early. So the way we're going to do that is we're going to keep updating current.next, and we're going to update count by 1 each time. But then we know to stop because we say, okay, we're here where count is 0. Then add, if we're here if count is equal to 0. Well, the first thing to check is something like if index is exactly equal to, or sorry, if count, which is 0, is exactly equal to index minus 1. And you could already see where we would have an issue if we were looking for index of 0. But we'll take care of that in a minute. Instead, we're going to say, in this case, we're saying while current is not none, well, it's not none, is count, which is 0, equal to, in this case of index, we're looking for 2. So is it equal to 2 minus 1, which is 1? No, it isn't. And because of that, we don't do this next part, which I guess I'll put in the else statement. So we'll have something here eventually. So if count is not equal to none, it's not. We keep doing this. I say, is count, which is 0, equal to 1? Because we want the number right before the index. No, it's not. So add 1 to count. So now count is 1, and move current to current.next. Now count is 1. Is count, which is 1, equal to 2 minus 1? Yes, it is. So we're actually done. And in that case, we'll just break out of the loop. So at this point, or maybe we don't even want to break out of the loop. We can actually just do it right here. As in, if this is the case, at this point right here, we don't need to move forward anymore. I can say something like, oh, well, count is equal to the index minus 1. This is where I want to add it. So current is currently pointing here. And let's say at this point we make our new node, because maybe we don't make it before because maybe we're not able to add it. We haven't really worried about the error cases and the edge cases. So here I write node val. And now I have a new node like this. But how do I hook this up here, given what we have? So if I were to like move this forward, something like that, last still points here. So how do I hook this in to where I want to insert it at?
So wouldn't current dot next equal the new node and then new node dot next equal the next node? Or
This is where it gets tricky, right? So
I think new node needs to point to the other one first so that we don't lose it. And then current can point to new node.
yeah, so the first thing we might want to do is say, okay, we have the new node already. New node has a next, but it currently points to none. Well, we actually want to point that to it, not to current, because that's going to be its predecessor. We want to point it to whatever current dot next is. So we say current dot next. Current dot next is here. Now new nodes dot next points to the same place, which kind of makes sense because current next is that. Whatever current's next is going to be the new nodes next. So now that we've done that, that's why the order often matters and why drawing it out is helpful. Now that we've done that, how do we actually, put this new node within the flow of the entire linked list?
It'd be current dot next equals new node dot next or equals new node.
Yeah, exactly. So current dot next is going to be equal to the new node we just created, but we did it in this order because otherwise we would have lost access to that. And at that point, let's say insert at doesn't return anything. We're done. So we could just say return. We don't have to return anything. We could say like break if there's nothing at the end of this, but this way we know, okay, we found it and we're done. And this will now work. So we put a 5 in there, and this will work in most cases. So based on how I have it right now, like let's say I wanted to insert at the first position. I inserted it at the first position. We've seen second. We've seen, well, we can see third. What if I wanted to insert it at the fourth position? Does that work? That works. There is no fifth position, so I wonder what would actually happen there. Just nothing. But yeah, that's where we might want to start caring about like index out of bounds stuff. And then similarly, even though 0 is there, it doesn't work. And why doesn't it work? Because based on our logic, we say like, okay, count is 0, index is 0. If count is equal to -1, well, that doesn't work. And it doesn't work because this is a special case where if you want to add it if you want to insert it at the beginning, that doesn't make any sense. Like our thing is not prepared for that because we want to get the thing right before to hook it up. So we can just make that a special case where we say something like, maybe we, even right before any of that, we could say like special case, we say if index is identical to 0, we want to add it at the beginning. And we could write all that logic, but actually we already wrote that logic. We could say self dot prepend that. And then at that point we return because we don't actually want to run the rest of our code. So that now would work. So now it works for everything. And the only issue is, so in that case, I could say inserted at 0, 1, 2, 3, 4. What about 5? Well, that's the case now where once again, we might have this like while statement. If we find it, great, we do it. If not, we move on to the next one. And if we ever get to that case where current is now none, well, it doesn't make sense to add it at that point. So we'll just have the same thing we have here where I just, raise this index out of bounds error. And, especially on an interview, you generally aren't expected to worry about these like edge cases like index out of bounds, unless that's specifically what it's about. But it's kind of cool to see that like we can get just as much control as Python has with its own arrays. Cool. So we can't do out of bounds either. I suppose we could similarly, right before this, just like we have this here, we could add that there if we wanted. And honestly, a way to do that would be to first peek at it. So we could say, if you're trying to add to a place that doesn't exist yet, that doesn't make sense. So maybe I'll actually do that instead, where before I do any of this, the first thing I'll do is just say, you know, assert, or I guess I don't even have to assert. I just say peek at the index, self.peek at the index. And maybe I just write a little comment there for why I'm not doing anything with it. Assures index exists, otherwise raise error. And now that actually takes care of any of those issues where, you know, now if I try to say insert at position -1, we get the can't use negative index. And if I try and insert at something that's too big, we get the out of bounds error. And otherwise, wait, is 4, insert at 4, is that out of bounds? I feel like that's inbounds. Why is that a problem? Yeah, maybe that wasn't the best way to do it, because I seem to have an issue there where why is that the case? As in there's 0, 1, 2, 3. Okay, got it. It's sort of like, yeah, so it's not a perfect solution. I would want to make some way, I guess peak is a little too strong there. I actually don't want to rely on peak, I guess, because by its nature, it might be the thing right before. So maybe I'm just going to take out all the out of bounds type assurances for right now, and we'll just say, okay, we don't have that. Okay, we're gonna look at the chat quick. So could you explain lines 45, 49, and 50? Those might be different lines now, but we can. So
yeah, I was just confused about like when we were actually putting in like the new node, I understood like us connecting it to like the next node, but I was a little bit confused on like how current, I guess, connected to the new node. Like the lines just didn't make sense to me.
Yeah.
I'm not sure how to explain it.
No, that's fine. I feel like we can do it again, and you might be able to see it this time. So
Okay.
Current, let's actually walk through it. What happens? We'll ignore this for now. That's like a special case, but count is going to start at 0, right? And current starts at whatever head is. Okay. And now I say, while current is not none. Well, current is not none. So I walk in here and I say, is count equal to index -1? So if I said, is count equal to index, I'd basically be trying to find that index I care about, in this case 2. But I actually want to find out the index right before, because if I get to this point, it's too late to hook things up. Whereas at this point, I can hook it up between those two things. So really, I want to put it right here. So it's here I care about, not here. So does that much make sense?
Yeah, that makes sense to me.
Okay, so we're gonna, if count is equal to index -1, I do something, but right now count is 0. So an index is 2, so index -1 is 1, so 0 doesn't equal 1. I hit the else, I say add 1 to count is now 1, and then update current to current.next. So current points here, and it has a .next. I'm now going to move this pointer current to point to whatever current.next points to. And that is a little confusing. And it's going to be the same thing we do later. So it's sort of like you read it right to left, where first you look at current.next. Current, you follow it here. .next, you follow it here. This, the node with 1 is current.next. Then on the left hand, when you say current equals, you're saying take this value current, I don't care what it currently points to, point it to that thing I just told you to point it to. So we evaluate this first, and then we point it to that next thing. Okay, so once we have that, well, does that much make sense? That whole, like, this idea that you're, does this line make sense? Because it's kind of like there is a fair amount of, there's an idea in there that we just get used to as programmers, but it's not necessarily intuitive. So does it make sense why current equals current.next moves the current pointer from this node to this node?
Yes. Yeah,
Okay.
I got that now.
Okay, so now current points here and count is 1. So I say, okay, count is 1, index is 2, 2 minus 1 is 1, count is 1. Oh, I'm actually where I want to add the thing. So now we run the code to add the thing. And the first thing we do is we just make a new node and point that to this newly created node val. So that's this right here. I have a pointer, I'll put it up here, I guess. I have a pointer called new node. It points to this node 5, and 5 itself, this node, has a next which just points to nothing, because that's how it's defined up here. If we don't give it, next is just none. So this line just creates this thing, but it's not part of the flow yet. And then the sort of like, little dance we do is we say, okay, we only have a few things we have access to. We always have access to the head. Doesn't seem useful right now. We always have access to the last. Doesn't seem useful right now. We have access to the current. Current points to the thing right before. So how do I make it? So, I mean, this is what it looks like right now. And ultimately, I'm going to want it to look like this. So how do I make that happen?
So the new node has to point to the next node, so like the 2.
Yeah. So we might be tempted to do this first, where we say current.next over here is equal to new node, right? So let's say we did that. Let's say we don't have this other line, and we just say current.next equals new node. Okay, we could do that, as in we take current as it is, we take its dot next, we don't care about what it was pointing to, now it's pointing to new node. The problem is we lost the rest of the list in doing that. So we have to have some way of preserving that other leg of the list. So if we go back, this is what it looks like right now. Something we could do is we could say something like, if we wanted, we could say, just make a new variable. We say something called temp. And temp is going to point to whatever current.next currently is. So that's assuming we didn't run this yet. Something we could do is something like this, in which I say, okay, I'm making this thing called temp right now, because we can make as many of these variables as we want. So I'm making something called temp, and that points to whatever current.next points to. So it points here. And now I always have access to this. And now if I wanted, I could say current.next equals new node. So it points here. And now where would I point this, given what we have?
It would need to go to the temp, so 2.
So we say, like, first, what is this called?
The new node?
Well, new node is the entire node. So we could say like new node.val, and that's 5. But what is this?
New node.x.
Exactly. So that's new node.next. And where do we want to point it?
To current next. Okay, I get it.
Yeah, well, in this case, we're pointing it to temp because we made something called temp.
Mhm.
And that works too. But if we go back to the way we had it, it turns out we had enough without the temp. We just have to do it in a specific order. So if we have something like this, we could say, okay, instead of temp, before I do anything, like, I'm not messing it up if I say, okay, well, current.next points to 2. It points to the node with 2. Well, I can say current.next, that points to the node with 2. Well, new node, which it has a next, but it currently points nowhere, that points to whatever current.next points to. So now they both point here. And technically that's like a kind of thing, but because we want this to be a list, at that point we say, okay, the current dot next, when we were referring to it on the right side, we were saying, okay, what it points to. When we refer to it on the left side, we're saying move it somewhere. So at this point, now that we've already set new node dot next to what we want it to be, now we could say current dot next, and where do we want to point it? We want to point it to the new node itself. But you're not wrong that it's a little tricky, which is why drawing it is so useful, because drawing it lets you see it in terms of arrows, and it's very confusing otherwise.
Yeah, that definitely helped. I understand it a lot better now.
All right, cool. Well, if we want to continue, I'm just starting to realize, did I start this very early, or how long have I been going for? Because I see it's 3:44 right now. I must have started at like 3, right? It was 3:44 my time. Wait, what time did I say I would do this? I said I would go from 3:30 CST to 4:30 CST. Okay, got it. I mean, I could keep going. I don't really, technically, I'm on the clock till, let's see, 4:30 my time. It's 3:40 my time. So I'm good to go for another like 45 minutes. If you guys want that, we could, the next thing we could do, because it really hones in this, this intuition around linked lists, the next thing we could do is remove. Does that sound good? Okay. Well, I mean, we could write something like, you could start to see how you could write different things where, in this case, I did like insert at, and I could do something like remove at. But just as well, I could write something like, remove value. And then I give it a certain value and it removes the first thing with that value, or remove all value and it removes everything with that value. And these are all, useful things. And just like append and prepend, I could have something like, instead of, append, which means add to the end, I could have pop, which means remove from the end. Similarly, instead of prepend, I could have something like, in JavaScript, they call it unshift, which is a very weird word, but it means remove something from the beginning. So yeah, I'll leave it up to you. What's something we might want to implement? Do we want to remove always from the end? Do we want to remove always from the beginning? Do we want to remove at a given index? Let me look at the chat. Does anyone want to see a particular thing?
I was hoping we could touch on non-binary graphs and
yeah. Fair enough.
GFS.
We can move on from this at this point. That's fair to me. So I have this open here about the depth first versus breadth first search. So I've not actually written that, which I hope I can do it in real time. But as you'll see, it's sometimes a little tricky, but it'll be good to see. So let me just make a new file, and I'll call it, binary tree.hide. And to do this, let's do a similar thing where the nature of this binary tree is that it's going to have, like, I guess I'll make a class binary tree, and this is not a binary search tree necessarily. There's no guarantee about the order. It's just, it has stuff in it. And so my binary tree is going to look like, I guess, what does the constructor for my binary tree look like? I didn't actually think of this as in what,
We still need a node class, right?
well, yeah, I mean, the way I think of it, like a binary tree can represent either the leaf or the branch. So it's kind of both, as in, if I make a binary tree and I give it just a value, that's a tree. But if I also give it a left and a right, now it's a branch. And so maybe we would, have defaults there where we say like, okay, by default, left and right are none. And then like usual, I'll just say something like self dot val equals val, self dot left equals left, self dot right equals right. And in that case, if I wanted to make a binary tree, I could write something like this, where I would say like, okay, binary tree. What does a binary tree consist of? I'll open it up like this to make it a little simpler to read. I'll say like, okay, well, let's say we're trying to make this tree here. Is that what they're doing there? I mean, they're showing us the order of traversal, but let's say we're trying to make a tree that looks exactly like this, as in the parent has 1, the left child has 2, the right child has 5, and on and on. So I would say something like, okay, well, the root of this tree has 1, and then it has a left. Well, the left is a binary tree. And what does that look like? Well, it has the value 2, and it has a left and a right. Its left and right are themselves binary trees, but because they're leaves, I'll just write it like that, because left and right are going to be none. And then like that, we have 4. And then similarly here, the left of our tree looked like that. Well, the right of our tree is going to look like a 5. And then its left will be a 6, and its right will be a 7. And this tree is exactly the same as this tree over here. The problem is essentially printing it. So we can visualize like this, but if we want to print it, we might want to do something like, if I were to print it, I might do something where I say like def string self. And then really, I might want to print it as an array or something. And it's sort of like I'm printing at each level. So I print 1, and then I print 2, 5, and then I print 3, 4, 6, 7. And any level that isn't there, I just I put null. If it were like, let's say it had a 5 pointing to a 7 as the right, but the left was nothing, I would just say null. So maybe to print it, I would make like as list and make that an empty list. And I would say something like, the funny thing is, to do this, it's almost like we want to figure out this depth first or breadth first search. So the first thing I want to ask is, does this make sense? As in defining this binary tree, do we believe this is the same as this over here? Does that seem reasonable? Anyone have any objections? Okay. So the point of this depth first search thing is really about order. So these numbers here are not actually representing what's in there. It's representing the order it's looking at. So there could be anything in here. But the idea is that if we look at depth first search, we're looking at that root node, and then we look at its left child. And basically there's 2 ways we can go. In depth first search, we want to go depth first. So we look at the root node first always, and then we look at its left child. But before looking at its right child, we look at the left child's left child. Then we pop back up and we say, okay, look at the right child of that left child, pop back up, pop back up. Now we're back at the 1. Now we explore this one. And then after exploring this one, we explore this one and this one. So does that concept, first of all, make sense? As in we're looking at the root, and then we're looking at the left child, and then we're looking at all the left child's children before we look at the right child, and then we look at the right child, and then we look at all of the right child's children. And so
okay, so we create a stack, and then starting at the root, we push the root to the stack, and then we move left, and then we push that node to the stack, and then we go left again until we don't find anything. We keep pushing those to the stack, and then once it points to none, then we just pop that off and then go to the right.
Well, you're getting into the implementation details. Maybe that is the way to do it, but I was not able to follow that. But before we get into the implementation details, we just want to understand the core concept. As in, if I'm looking at this depth first search thing, I'm going like, I end up looking deeper first, as opposed to if we look at breadth first search. In this case, I'm looking at everything at the first level, then everything at the second level, then everything at the third level. So those are two very different ways of approaching something. One, you follow the rabbit hole as deep as it goes, and then once you get all the way to the bottom, you pop back up, follow the right rabbit hole, pop back up. And in this case, we're actually looking at it, yeah, one at a we're looking at each level one at a time. And you're right that it relates to these concepts of stacks and queues because that's one way to think about it. So even though we never officially went over stacks and queues, this is built-in functionality for Python arrays. We just basically use functions like push and pop to simulate it. So if I have this binary tree here and I want to search it, depth first search, maybe I'll have something like that here where I say DFS. It's not actually going to take anything, but the idea is it's going to print things in this depth first search order. So in the case of the tree we have here, I would expect it to print 1, then 2, then 3, then 4, then 5, then 6, then 7. So let's see if we can do that. So we're starting with this tree, and then I'm eventually going to say tree.dfs. And let's just say that actually does the printing for us. So right now, this isn't going to do anything. Let me just write pass over there and run it just to see. So if I say Python binary tree, nothing happens. But I actually want to see what happens when I run this DFS. So first things first, this is, DFS is run on the binary tree, and we're going to run it at the root of the tree. So the first thing we're going to want to do is print that. We'll say print self. Oh, give me a second. My alarm's going off. We'll say print self.val. So if I run this now, well, I print 1, but I want to print the rest of it. So remember, this is the root of the tree, and we might end up calling this recursively. Maybe not. Maybe we want to use this stack idea. So I'm going to print the root of the tree, but then what do I want to do next? After I print the root of the tree, what do I want to do? Do I want to print the left? Do I want to print the right?
Go left.
Yeah, it looks like we go left. And so I could just say print like self.left. But another way to do that is to call this recursively. So I say self.dfs, and then I actually pass self.left there. So what this is going to do is first it's going to print that root node 1. And now it's going to call this DFS recursively with this being the tree. And because of how this works, it's going to call, it's printing self.val, which is 2. And then it's going to call DFS on the left of the tree, which is 3. And then it's going to print 3. And then it's going to call self.dfs on the left of the tree, which at that point will be none. And then it's going to print none. No, actually, it's not, because it's going to print none.val, and that's where it's going to break. So let's actually see that. Before it broke, what happened? Why doesn't it? It takes 1 positional argument, but 2 were given.
Oh, because we don't have the val in the definition of DFS.
Why should we? It says,
Because you're calling it recursively.
Shouldn't you have a return in a DFS?
oh, wait. Nope, I think I got it. It's this. It's self.left, because self.left is itself a binary tree. We just call DFS on that, just like here, where we said tree.dfs, we say, self.left.dfs. So because this is a binary tree, we call it like that. We don't actually pass anything. Okay, so that will now work, but it's going to break once we hit that none case. So let's see that. We printed 1, then we printed 2, then we printed 3. Then we called self.left, which was none, and we tried to call .dfs on it. It doesn't have that because it's none. So we actually want to do something there where we want to say something like self.left.dfs if self.left. Do I have to add an else there? You can't actually. Yeah, okay, so I'm actually going to write it like this, where I'm going to wrap it, where I'll say, if there is such a thing as self.left, so if that's not none, then print it like so. So now let's try that. What happens? We print the 1, we print the 2, we print the 3. Okay, so we printed self.val, which was 1. And then we said, if it had a left, run self.left DFS. So then it printed 2. And if that has a left, it will print self.left.dfs. So it printed 3. And then if none, well, that's not true. So it skips this. Okay, so it skips this. We printed 3. We're done now. So this can get hard to picture because we're doing that recursion thing. So really what happened is we printed the 1, and the calling DFS on the root was not done until we ran self.left, which self.left.dfs, and that wasn't done until we ran self.left.dfs. And then that printed 3, but because this is none, now that's done. Now we're popping up to the situation in which we printed self.val, and we can visualize this if it's confusing, because it is. But basically, after we print self.left, I can ask something like if self.right, then at that point, self.right.dfs. So the way this is going to work, let's see, that actually prints the whole thing now. And that works, but let's visualize why it works. So we didn't even have to use this data structure of a stack, because recursion was enough to do it for us. In practice, if it was a really big tree, recursion is not always a great approach, and a stack basically mimics recursion because a recursion works on a call stack. They're the same concept, but let's look at this here. So I'm going to go here, and I have that whole tree there. Same tree from here, which can I copy it into there? Let's see. Yep, awesome. So the first thing I'm calling DFS down here on the entire tree. So the first thing we do is we print what is in the root of the tree. So tree.val is going to print this 1. And then I say, if there is a self.left, print on that tree. So it's like, So yeah, I'm going to paraphrase the tree by just representing it by its root. So when I say 1 here, what I mean is the whole tree of 1. So, and everything below it. So I'm going to say DFS, even though this isn't exactly how we call it, sort of like that. So I'm calling DFS on 1, and the first thing that does is it prints 1, and then it checks if there is a left. There is a left, this whole subtree 2, and then it calls DFS on that. So it's like before I can finish, before I can finish running that, like, because this, I'm still calling DFS on the first one. It printed the first thing, but it's not done running. First, it needs to finish running this before it can move on. So now I called DFS with 2. And then when I called DFS with 2, that printed 2. And then it said, well, does that have a left? It does. It has a left called 3. So at that point, I print 3. Move this down. Okay, and then at that point, I print 3, but then I say, does 3 itself have a left? No, it does not. Its left is none, which means this doesn't run. And then I say, does 3 itself have a right? No, it doesn't. It's a leaf. It has neither left nor right. So this doesn't run either, which means this whole DFS 3 thing is done running. So now that this is done running, we pop back up to the last thing we were doing, because the thing that called DFS 3, even though we don't return anything from it, was this call to DFS 2. Well, DFS 2 said if it has a left, in this case its left was 3, print it. Well, we did that. So now we move on. We say, does 2 have a right? It does, so call DFS on that. So now we do the same thing. We call DFS on 4. And because 4 is a leaf, we print 4, but pretty quickly we're done with it. And now we pop back up to DFS2. Well, we just ran this. That's the last line for DFS2. DFS2 is now also done. So now we pop back up because DFS2 was called from DFS1. And now DFS1 makes it, because it's done running this, can now run this. So it calls it for 5, and 5 in turn calls it for 6, and then 7. So that is a little awkward in the way that recursion is. I wonder if it would help to try this on Python Tutor just to see it. So pretty good tool for thinking about recursion. Okay, so cool. So I'm actually going to move my entire binary tree into there like this, my binary tree definition. And then I guess I will move my example binary tree in there. And then we're actually going to call tree.dfs. And now let's visualize that. Okay, so we're going to walk through it one frame at a time. That first thing, it now knows there's this thing called binary tree. Now it's actually going to define an individual tree, and it's going to use a init to do that, which is a little time consuming, but that's apparently most of our steps here. Oh, oops. Okay, we're already at DFS. I don't want to do that yet. Let's go back. Okay, so before we run DFS, let's just see. We have this thing called tree. So binary tree here points to the actual definition of the object, but tree points to my tree, and my tree is a tree. It has a val called 1 and a left. It's a little confusing, but the left is over here with a val called 2, and its left is 3, and its right is 4. And they, if it's a leaf, the left and rights are none. And then the right is the 5, and its left is 6, and its right is 7. So it's exactly like we pictured it, but this is what it looks like in code. And that's what it is. It's just things pointing to things, pointing to things. Okay, now let's actually run our DFS. So here we are. We're going to run tree.dfs. We enter into that line. So the first thing we do is we print self.val. Well, here's self. It points to that root of the binary tree. Print val. We print 1. There it is up there, if you can see it. And now we say is self.left. Okay, here's self. Here's left. Does it point somewhere? Yes, it does. So that is true. We enter in self.left.dfs. So now this is where it gets a little confusing with the recursion. Then we have a second thing called DFS now, which is going to do that over here. And now that's going to do the same exact logic where we print 2. And then we check if that has a left. It does. And now it's called DFS again, but I guess it can distinguish. It's going to print 3. And now it's going to check. So it prints 3, and then it checks if it has a self.left. No, it does not, because we're pointing at this one right now. We check it's right. No, it does not. Okay, return value none. So even though we're not explicitly returning anything, we're done with that DFS3. Pop back up. Now we're doing the self.right for DFS2. So we're at that line of code. So we finished this line of code for DFS2, which resulted in, self.left DFS3. So now we're looking at the self.right for 2. Okay, we're going to walk in there. We now actually call, we create this new thing DFS. It's looking at that right. It prints 4. And then it sees left and right don't exist because it's a leaf. Okay, it returns none. We pop back up now to the DFS2. It's still pointing there, but it itself now is done as well. It returns none. Now we're pointing back to 1. And the same thing. We look at its rightmost thing because we're at that line now. When we go in there, it prints it. It looks at the left first. And its left is a 6, so it prints that. And then that has a left and right of none. Those are done. pop back up to the 5. Now it looks at its right, it prints a 7, its left and right are none, so it's done. Pops back up to the 5, that's done. Pops back up to the 1, that's done. Now the whole thing is done. So thinking that through is definitely annoying, but that is, you know, it is sort of elegant that there was a lot going on there, but with recursion, we were able to pretty straightforwardly walk through that list in that order. So any questions on depth first search? Even though we're not getting questions, I hope it is at least useful to have this, and the fact that we'll put it up on video. So any questions before we move on to trying to do breadth first search? Because breadth first search is, you know, you don't really have one without the other. So we tend to compare them. Breadth first search is this idea where we're walking through it, where we descend as far as we can before looking at the you know, we descend to the left as far as we can before looking at the right. And breadth first search is a different idea, an alternative, which I'll put here in Excalidraw, where we want to look at everything at the first level, then everything at the second level, then everything at the fourth level in that order. And from my memory, breadth first search is harder to do. I don't think there's a nice little recursion way to do it. You need this idea of a queue. So you actually already know what a queue is because you've waited on lines in your life. You definitely know what a queue is if you're British, because that's what they call lines. So a stack is this idea that, like, you know, if I put a book down and then I put a book on top of it and then I put a book on top of it, the last thing I put down, the top book, is the easiest one to take off. So a stack builds up like that. A queue is just its opposite. And it's what we're most used to. First in, first out. So if you get on a line, if someone else enters, they don't go before you, they go behind you. Next person goes behind them. The next person goes behind them. And then when whatever they're waiting on a line for, you know, the DMV or something, the first person that's ready to be taken, it's the first person that goes, the first person that arrived, and then the second person that arrived, and then the third person that arrived. And that's actually the most natural way to think about things, except in computers, stacks tend to be more natural. I think just because of the way recursion works. But you know what a queue is, and an array basically mimics a queue where, you know, every time you add to the end, you're adding to the end, and then the first element remains the first element. So let's see if we can make a breadth first search. And instead of actually implementing a queue, I'm just going to use an array or a list in Python. But I'm going to say Python list so I can actually see what functions are on it. How do I see that? Like this maybe. So I see I have list.append, which means add to the end. Removes the first item from the list. Okay, no, pop, remove the item at the given position. So I see that arrays are good at adding to the end and then popping the last one. I could always pop the first one. It's probably just a little inefficient. I know there's this thing called DQ in data.collections for Python. So while we could use the regular list, this DQ is actually going to get us, you know, the runtime we want for a queue, which is like constant time for taking something from the top, I believe. I would need to see how to use it exactly. So pop from the right side. What about from the left side? Pop left. Okay. So maybe I'll actually do that. I'll do, they have an example of people using it. Yeah. So let me actually try that. I'm just going to right in here, grab, because this is eventually what we will do in the course, where you don't often write things totally by yourself. You actually use something that already exists. So let me just try it out here. Let me put pass there now. This is my tree.dfs. Comment that out for now. But what if I just want to try out this DQ thing? I'll say D equals DQ, just like they did. And let's say I'm going to start it out empty. I believe I could do that. And then I'm going to say something like, I want to, because this is a queue, I want to add things to the end, let's say, and then keep getting them off the end. So append will add to the right side. That's what I want. So I'll say D dot append 1, and I'll just keep doing that. D dot append 2, 3. And then I want to pop off that thing on the leftmost side first. So even though I add to the right, that's the order they come in. The first one to leave should be the one all the way on the left, and that's called pop left here. So now if I say something like print D dot pop left, if I do that over and over, I should print 1, 2, 3 in that order, whereas the standard pop would print 3, 2, 1. So let's see if that works. Okay, that's satisfying enough to me. So I'm going to try and use this DQ to do exactly what it says here. So what it says here is that I have this queue, and as I get things, I add them to the queue. Okay, I think I understand, but let's try and implement this. So ultimately what we're going to call now is not tree.dfs, but tree.bfs. And given this tree we have, given this tree, it should print 1 first, then 2, then 5, then 3, then 4, then 6, then 7. That's how we know that it's working. And if we wanted to make it look like this tree, then we could actually say, okay, in order for it to print in order, it should look like this, 4, 5, 6, 7. So we know this is working if it prints in order. And we see that DFS is different. So if I do this right now, that's not in order. We want that, based on how we wrote them, BFS will run in order. And just to explain, the reason why there's 2 types is because, think about it like the internet or something. The internet is a type of tree, basically. It's really a graph because you can have loops, but if you have a website and it has links, you can follow those links. And maybe if you follow those links, you get to a website that has other links, and then you could follow those links. So the difference between depth first search and breadth first search is depth first search says, okay, here's a website. That's my starting point. That's my route. Find the first link on that page. Now follow it. Find the first link on that page. Now follow it. Find the first link on that page. Now follow it. And you're prioritizing that first link and following it compared to prioritizing, like in breadth first search, it would say, here's your website. That's your route. Now follow every link on this page. After following every link on this page, follow the first link on every one of those pages. And only when you're done following every link on those pages do you then follow whatever they link to. Which might make sense, might not, but it's exactly this. It's saying it's a little harder to tell when the graphs are smaller, when the tree is small, but depth first search preferences following something all the way to the end before, looking at the other options. Breadth first search preferences looking at that first level, then the second level, then the third level, so that you don't go too far before, seeing everything that level has to offer. Okay, so here's my breadth first search. The first thing I'm going to do is, because I know I'm at the head, or I'm at the root, I do the same thing I do there, print self.val. So the second thing is, how do I follow it? Well, at that point, I might want to have this queue idea, and I add things to the queue. And I'm realizing what I actually want to do here is I want to take that DQ, and it's not normal that you would have this intuition, because I didn't have this intuition when I saw it, but it turns out this is a way to do it. So I'm going to have that DQ, and I'm going to call it, what should I call it? BFS, or I'll call it nodes to, I'll call it node Q. That's enough. It's just the nodes in order. And you'll see DQ, you could actually give it an iterable first. I think you can just give it an element. So if I say self dot, or if I just say self there, it's actually going to have something in it. So at that point, if I were to say like node q dot, and I wonder how you get the count, okay. So I would say node q dot count there, and I were to print it, I believe it should already have something in it, which is that first root element. So let me see, binary tree object is not iterable. Can I just put something inside there? Maybe not. So maybe I do this, I say node q, and then I say node q dot append, which will append to the end, but there's nothing in there yet, and I say self. And now I just want to print the size. Count takes an argument. Why does count take an argument? I guess I have to look at this collections thing. I don't know if I want to know how many things are in there. Okay, that's the number equal to X. What if I want to know the length? How do I know the length? There must be a way, right? Or just I want to know that it's non-empty. There must be a way to know that it's not empty. I see that if I try and pop something and there's nothing in there, there's an issue there. So I would hope there's some kind of peak. How do I know if there's something in there or not?
Could you just do length?
I don't know that it has a length. It would have told me if it has a length. Because this isn't necessarily an array. I'm surprised. I would assume there would be a way to tell whether it's currently empty or not. And if I said something like max length, I think that's like an implementation detail. I don't think that's what I actually want. I don't think that's the actual length. That's the max length. I think I might want to just go back to using a list, and even though it's inefficient, I'll just keep grabbing what is, I'll keep popping that first element. So I can do that. By the same token, I'll take this out for now. I guess I'll still call it node q, but I'll make it a list. And just to see that that works, so I have node q and it's a list, and the first thing on there, the first thing I'll put in there is self. And at that point, I should be able to print self dot or len around self. I think I'm realizing you're right. Okay, wait, that's it. I can do it exactly this way, but I forgot that in Python, you have the general len operator. So that's probably what we want. Yeah, so that's how I know that there's something in there. Great. So currently there's just self in here. And because there's something in here that's good, what I'm going to do is I'm going to have a while loop. And I'm going to say while node q, while the length of node q is greater than 0. So once it's 0, this while loop will end. But while it's greater than 0, and we currently have something in there, while it's greater than 0, the first thing I want to do is say node q dot pop left, and that will give me the leftmost thing, which doesn't really matter right now because there's only one thing in there. But we want to add things at the end, and we want to pop them from the beginning. So I'm going to say node q dot pop left, and that's going to return me this root, which I'll just call it current or something, or I'll call it current. And then at that point, I'll say print current dot val. So that was a very roundabout way to do it, but it's going to be useful for doing the other ones. So let's just see that right now. We are printing 1 because we have this node queue, we add to the right of it 1. And then we say, while it's non-empty, the first thing I do is I pop that 1, and then I print its value. And then before I'm done, what I want to do is I want to take that same node queue and I want to push onto it. Did I get that right? It's not push, is it? It's append. I want to append onto it both current dot left and current dot right in that order. And I don't think it actually respects this way I did it. So I'm going to make it 2 separate appends. So I believe if I'm doing this right, and one way we can see this is actually to print the node queue each time. Although I guess we would just see the memory address of the thing. So maybe actually in order to print it, I'll just add a print statement here for the binary tree, which I'll do like that, where I'll say, if I want to print a binary tree, I just want to say, just going to return something like tree, tree with root, and I'll just define it by its root value, which is fine for the way we're doing things. So now I could actually print, saying while this exists, I want to print the node as it exists. So if I were to say print node queue, I just want to see what it looks like. Okay, let's actually try and run DFS right now. Maybe it runs forever because I didn't do it right, but do we get anything here? Because it would be nice to see my output. Well, I see DQ and then I see there's a binary tree in there. It's not printing that. And I kind of would like it to see what's in there. I mean, I guess this isn't worth printing because as you can see, as it turns out, this was in the right order. So maybe we'll just, it breaks at a certain point, but okay. It is printing 1, 2, 3, 4, 5. Why? Well, I have this node queue thing, right? And that's going to point here, and that's going to point to essentially a list, which I'll represent like this, and I'll just put them next to each other. So let's just say it's almost like it points to an empty list. We don't know how big it is, but it points to an empty list. The first thing I do when I create the node queue is I append the binary tree beginning at 1 with it. So I'll represent that like this to say the entire tree, not just that value. Make it a little smaller, I guess. I'll make it. Make these bigger. Okay, so I'm putting the 1 in there. That's all that's in there right now, and its length is going to be 1. So while the length is greater than 1, I say, okay, current equals node q.pop left, which means I pop this and I'm calling it current. So when I pop it, it's not on the list anymore. The list is now empty. If we were to immediately run this while loop again, its length is 0, which is not greater than 0. Okay, so then what I do is I print current.val. So I print 1. And then I add to the end of the node queue left, and then I add to the end of the node queue right. So in this case, 2 is on the left and 3 is on the right. So it looks like this, where the first thing I added was the left thing, which was 2. And then after that, I added the 3. And now I'm done. So I go back to the beginning of the while loop. The length is 2, which is greater than 0. So I pop the leftmost thing. This has already been printed and it's done. So now I'm looking at 2. And because I popped it, it's like, this is now the first element. So I'm looking at 2, I print it. So now I printed 1, now I print 2. And after I print 2, I add 4 and 5, which are its children, to the list. So now my list looks like this. 4 and 5. Get rid of that. Okay, so I do my next iteration. The length is now 3. I pop current, which is 3. I print 3. And after I print 3, I add its children left and right to the queue. So now 6 is in the queue and 7 is in the queue. So I printed 1, 2, and 3. Now I pop 4. So I keep moving these over, but in reality, the queue just takes care of that. So I'm not doing any shifting actually. So now I print 4. But now I say, okay, append current dot left to the list. Well, current dot left is none. And that's going to start breaking my algorithm. So even though this all works, it eventually breaks because I'm trying to do the same thing on none. So I just need some kind of base case there where I say something like, if current dot left, then do this. Otherwise, if current dot right, then do this. And if either of these was none, it just wouldn't add anything to the list. So now if I run it again, it runs it correctly. And so, yeah, that's the difference between breadth first search and depth first search. As you see, they're both pretty small little things. It's just a matter of how you're keeping track of something to print, basically to print things or to visit things. So in this case, it's very natural with recursion. And honestly, if I wanted, I could rewrite it using the same DQ thing where I could say like, I have a, I think I could do the exact same thing. I would just say I have my queue and the first thing I'm adding to it, but it's not a queue. I'll say, or in this case, I'm thinking of it as a stack. Even if this collections library is called DQ, it supports both. So yeah, that's kind of a fun thing. I'll do it in exactly the same way. Where I'm going to say, while the length of that stack is greater than 0, well, it currently has something on it. The first thing is to take that stack, and I guess I have to think about this for a second. The first thing I want to do is pop the leftmost, or pop just regular pop. I think I want whatever's on the right. And then I print it. And then in terms of adding, I can add to the right, and I add another thing to the right. So let me see, does that mimic this functionality? Or let's see if we can get DFS right like that in Excalidraw. So now we're calling it node stack. I guess if we want to go back, it's going to be, what was the case for DFS? 1, 2, 5, 3, 4, 6, 7. So if I do DFS now, I want that to print in order. So let's think about it. I have this stack. The first thing I put in it is just that 1, right? So let me grab this picture and move it down here. So the first thing in it is the 1. And then I say, while there's something in it, well, there is something in it. So pop, and pop is going to pop from the right by default. Well, there's only one thing in here, so that's what gets popped. I print it, so I print 1. And then I say, if there is something on the left, then add that to the tree. So I'm going to add a, and I'm always adding to the end, so I add a 2 here. And then I add the right at the end, like this. I'm starting to think this isn't right, but I wonder how I would do it more correctly. And in the next iteration, there would be 2. And then it would look at that 2 first. Well, I think it's that I want to, it's almost the opposite. Instead of pop left and append, I want to pop and append left. Is that right? I don't know. I should probably just leave it how it was. It was working. Sometimes that's the right approach. But this same idea of a queue, we could make a stack. And if we go to this site, it's kind of trying to tell us that we're just like it's saying DFS uses a queue. We look up here, it's saying DFS uses a stack where you add that first element, and then after it, you add the 2. And before moving on, you add the 3 and you add the 4. This recreates it. I see it's already 4:30 or 4:30 my time. So I guess we're done. But yeah, any questions, I'll stick around until we're done. I know I did a lot of talking, but hopefully that's a useful explanation of both some linked list stuff and breadth first search versus depth first search on a tree.
It is, thank you.
Cool. Ooh, anything else? Sometimes I get worried if no one's asking questions. But people seem pretty engaged, which is good, at least in the chat and stuff. Yeah, hopefully this is enjoyable. Hopefully everybody has fun weekend plans. I don't know. I'll stick around for another minute and then I'll go and then I'll leave and then I'll upload this and then I'll share that on Slack.
You have a good weekend, Ben.
Thank you. Appreciate it. Do my best. Okay, I'm going to sign off now and doing that. Do I end the meeting for all? I'm going to end the meeting for all. Sorry, everybody, if you wanted to hang out here. Ending the meeting for all, and then I'm going to upload it.